So basically, Gauss played around with this. He's a mathematician. I'm not sure he did exactly this, but his mathematical principles are used in this. Let's say we take an interesting electric field. So we have a point source of charge and we have a rod of charge. And we draw the electric field lines rather like we did in lab. And then I basically divided my diagram in two, and I did these at the top to show there's regions where there's a lot of arrows, and there's regions where there's a few arrows. Now, when we said, well, how many arrows shall we have? We just made up a number. Let's do 8 or whatever in lab. Okay, but the fact is that some of them were closer together and some of them were farther apart. As you do more, that variation becomes more distinct. And so you can imagine if I take a little loop, a little line, if you like, a little barrier, and I say how many arrows pass through that region as opposed to how many arrows pass through that region, I get a very different answer. For the same size loop, I get a very different answer. And that's meaningful. What that means is that when you get more electric field lines closer together, you have a stronger electric field. Remember, an electric field line is just the direction that the electric field points in. It doesn't tell you its own strength. But the proximity of the field lines to each other tells you a lot more about the strength. So I can say, oh, here the field is stronger because there's more field lines going through that little area than here. And that's kind of like meaningful. Here's the thing. If I draw my diagram correctly, carefully, I can actually do math on that. And so this is, in a way, the genius of Gauss. You're doing math on something, on a diagram, which is a visualization of an abstract concept. You're doing math on a diagram of field lines when the idea of a field line is an abstract concept. And it gives you answers that are right. And so this brings us back to this idea about models. You know, in some aspects of physics and science, you actually look and see and you describe it, you know. But there's other aspects of engineering and science where you basically, you see behavior in and you see behavior out, and you got a gizmo in between. And you didn't make that machine, you know, nature did, and so you can't know the mechanisms, but you know what's going in, you know what's going out. So as long as you make a machine that does the same thing, then it works. When they started doing, I think it was vision, I saw this thing years and years ago where somebody had built a model of how the retina works, using a whole bunch of wires and switches and stuff like that. And it gave results that were meaningful. Now, is it perfect? No. And eventually, if you get detailed enough work, you need to refine the model. So there's these two aspects. One is you can use models to represent real things. And the other thing is sometimes when we describe what we think are real things, we're using a model. So I remember having one of my physics teachers walked into class and said, "You'd be amazed at how many people still believe in the electron." And I was like, what? Did I miss class? What on earth is he talking about? And what he was trying to get across was the fact that our concept of an electron is just it's a visualization, it's a guess. And as long as our guess gives us answers that match with the experiment, it's very useful. But if there comes a time when our guess gives us answers that don't match the experiment, all we need is a better guess. You know, it's not that there's something wrong with the electron. The electron's the electron. It's just our model needs to be tweaked a little bit. And I remember as a student getting really upset when I found out that when they told me that you know, Newton's laws weren't really right and really we needed Einstein's laws. And part of me was, well, why didn't you teach me Einstein's laws from the beginning, you know? And then partly also it's such a small effect I didn't really believe it. But the fact was it was a small effect. And Newton's laws are great for 99.9% of what anybody does. It's just for that other bit we need to be a bit more precise. And so that's where we need to go and take into account Einstein. And maybe he'll run out of precision and we'll need to go something beyond there, you know. And that's a little bit of a hard thing to accept when you first begin. But don't go through thinking you're never going to make up an equation, you're never going to make up a gizmo that models a plant. You know, you're working in chemical engineering, you'll have some kind of gizmo that models what the plant does. That's not the plant, and you just, that's the way it goes. So we're going to talk about this. There's some new language. So again, always embrace the new language, because if you don't really embrace it, then you don't really get to it. We're going to introduce this idea of flux. If I talk about a flux of arrows, it means there's a bunch of arrows coming towards me. You know, it's like a flux of arrows, a group, what would be a, can't think of any examples, a pack, you know, a herd, a flux. It's like, you know. So electric flux, what is electric flux like in a uniform electric field? And then we're going to do a non-uniform electric field. And then we're going to play some games with it. And we're going to talk about a closed surface. And then we're going to talk about Gauss's law. And then we do other stuff. And there's no point in describing that at the moment because we're not quite there. So let's just talk about this. I am drawing my visualization of electric field by drawing electric field lines. What can you tell me about the electric field that I've drawn? Is it uniform or non-uniform, and how do you know?
Uniform?
It's uniform, and how do you know?
They're spaced out somewhat equally.
They're parallel as well, yeah. I think the key thing is the parallel. But you're right, if I go from area to area, they've got to be also spaced out evenly, yeah. But the key thing is the parallel. And if I imagine drawing the gravity lines in a room, the gravity lines all point downwards, don't they? The gravitational field lines all point downwards. But if I have the gravity field lines from the Earth, they're no longer parallel. You know, but that little room there is like that. So, you know, sometimes we need the convergence or the divergence of the field lines. It's significant, sometimes it's not, you know. Let's start off with parallel stuff, uniform fields. Let's make it more complicated later. So this is a uniform field. How many arrows shall I draw? It's up to, there is a, well, we're going to eventually decide, but for the moment we're just going to say we're going to do so many, you know. Basically, the more arrows, the stronger the field. Remember, the field line is just the direction that the field points. It's their proximity that tells you how strong or weak the field is. So, okay, the number of field lines in any given region represents the strength of the electric field. Lots of electric field, lots of field lines, weak field, little bit of field lines. And that makes sense. As you go further and further from the Earth, the gravitational field gets weaker, and the field lines get further and further apart, you know? So it makes sense. Imagine, into my imaginary diagram, I slip an imaginary card. Now, I make it so that the card is at 90 degrees to the field lines. And because they're parallel, I can do that. I say, imagine a surface that is perpendicular to the field direction. It's at 90 degrees to the field direction. The electric field arrow density, how many arrows per square meter, is proportional to the magnitude of the electric field. The product of the magnitude of the electric field and the surface area is called the electric flux. So this electric flux is this number I get, which is representing the strength of the electric field and the area that I'm taking that field over. So it really represents the number of arrows I have. Yeah. I'm going to say, what is that letter there? If I said to you, give me the Greek sound for that letter, what would it be?
That's phi, right?
So in my experience, in Britain and mostly in the States, I've always heard it said as phi, like PH, you know, phi, however you phi spell. PHI, but, you know, like your thigh, you know, not thigh, but phi, I guess, but, you know, it's phi. And occasionally I've heard people say phi, and I always thought they just mispronounced it because they were like, you know, not as smart as I am. And then I was teaching class here a couple of years ago, and it was an evening class, so the lights were down, and I said, what's that letter? And everybody said phi, apart from one student who said phi. And I looked at the guy. I said, well, actually, that's phi. And then I realized he was the only Greek student I've ever taught in my entire life. So I realized that he probably knows more about it than I do. So I said, so what's the difference? And he goes, yeah, it's just two ways of pronouncing the same thing, you know. So it's not that people, when they say phi, are ignorant. They just have a different way of pronouncing it. But most of the time, you'll hear phi. Most of the time. So, so basically, phi, which is flux, is equal to the electric field strength in newtons per coulomb times the area in square meters. So it's newton square meters per coulomb. Yeah. So electric flux is proportional to the number of electric field lines penetrating some surface. Just bear with me, it's going to get very useful. Let's say that by chance, for some reason, and there's a good reason why we're going to do it, we choose not to have the card at 90 degrees to the electric field lines. Well, that's okay. We think the area is this, but really the area is that. You know, it's the front edge, it's the cross-sectional area. And if I think about it, they're related pretty much by this angle. So if I have that, then that divided by that is the cosine of the angle. Agreed? Because it's a right angle. It's a right triangle, yeah? So the adjacent divided by the hypotenuse is the cosine of the angle. Well, if I have an adjacent area and a hypotenuse area, it's still the cosine of the angle. The adjacent area divided by the hypotenuse's area is still the cosine of the angle. So then I can say, oh, well, this flux is the electric field going through my little cross-sectional area, which is the electric field going through my original area times the cosine of the angle between them. Yeah? That's just geometry. Now, I've seen this form before when we did work is equal to F times D times the cosine of the angle. And we did this weird thing. We said, well, hold on, if F is a vector and D is a vector, then I have this dot product that made life a lot simpler. Let's do the same thing here. And we say, that's crazy because area is not a vector. I'm sorry, but area is a scalar. And the answer is, I'm doing math on a diagram of an imaginary thing. I think I can make up a vector if I want. And so we make up an area vector. And the area vector is an arrow which is perpendicular to the area and has a magnitude equal to the size of the area. And if you do that, so this angle here, theta, is the same angle as, if you work it out, it's the same angle as the angle there. So, so the angle between my front surface and my original surface is the same angle as between my field vector and my area vector. And so I can say, oh, this is the same as E dotted with A. Now the problem with area vectors is if I'm using my hand, is the area vector pointing out of the palm of my hand, or is the area vector pointing out of the top of my hand, the other side of my hand? And we've got to decide, and we're going to decide that in a few minutes. Okay, so don't worry about that. Let's do a couple of these. An electric field of 2 newtons per coulomb points in a positive x direction. So this is 2 newtons per coulomb. What is the electric flux that passes through a 3 square meter card that is in the YZ plane? Oh, okay. So apologies again. Physics says X and Y and Z, and math does not. This card is in the YZ plane. And let's just do it. My area vector is in that direction, so I'm going to call that A, which equals 3 meters squared. And this is my E. So I can say flux is equal to E dotted with A, which equals, if you like, E, A, cosine the angle between them. So my flux is equal to E, well, magnitude of E is 2, and the magnitude of my area is 3, and the cosine of the angle between them, the angle between that vector and that vector is 0, because they're parallel. So my flux is equal to 6 newtons per coulomb. There's my E, multiplied by meters squared. There's my A. So that's not bad. That worked out okay. Yeah, not bad. Make it a bit more interesting. An electric field of 7 newtons points in the x direction, 7 newtons per coulomb. This is my E. What is the electric flux of a surface that is 2 square meters if the normal to the surface is inclined at 70 degrees elevation above the positive x-axis while in the xy plane? Man, if there ever was a reason to have a diagram. There's the x plane and there's the y plane. So that's what it's saying. It's saying, don't worry about the z. This is my A, and this is 2 meters squared. So this is 7 newtons per coulomb in the x direction. This is 70 degrees angle of elevation above. So there's my angle of elevation above the positive x-axis while being in the xy plane. Because you could have this at some other angle processing around that pole. So I would not be inclined to give you a question with that language. I'd sooner give you a diagram, because that language is not trivial. That's why we have diagrams. So, okay, so we say flux is equal to E dotted with A, which equals E times A times the cosine of the angle between. So flux is equal to E was 7, times A is 2, times the cosine of the angle between. That is the angle between, so cosine 70. So flux is equal to, so the first thing we check is we're in degrees, 14 cosine 70. That's going to be 4.79 newtons per coulomb meter squared. So it's that guy. Cool. Not bad. Let's make it a bit more interesting. Electric field, I'm not even going to try and draw that to scale. You can do, but actually it's a little bit, it's not as helpful. Whatever your direction of your electric field, and whatever the direction of your area normal, there's a plane that goes through them. any two vectors lie on a plane. I have no idea what the plane is, but any two vectors lie on a plane. Let's assume that plane is my piece of paper. So I can just say, well, there's my electric field vector, and here's my area vector. And that will do it. I mean, as long as there's the two vectors, I'm fine. Now, I know that my electric field, this is actually 4I plus 2J plus 3K. I know that the value of that, newtons per cube, and I know that my area vector is 3I plus 4J, that's a minus, I'm sorry, the minus is at the end of the line, times 2K meters squared. Now what are the flux? Well, a flux is equal to E dotted with A. So my flux is equal to 4I plus 2J plus 3K dotted with 3I plus 4J minus 2K. And can you remember what you do for dot products? What do we do? Can you remember?
You do the matrix?
No.
Let's cross. Split.
You just multiply the coefficients together. You multiply like by like. So it's 4 times 3 added to 2 times 4 added to 3 times minus 2. So that flux is equal to 12 plus 8 plus minus 6. So my flux is equal to, what's that going to be, 14 newtons per coulomb meter squared. Notice, dot product is a scalar product. It cannot be a vector answer. So it's been a while since you've done a dot product, so go back and review it. And while you're at it, review the cross product, because that's coming up again as well. Okay? So not bad. From my own personal point of view, I kind of, as somebody who kind of like, my strength is more visualization. So whenever there's a way of working out so you don't have to do visualization, I always feel like, man, that's not fair, you know. Because it means that life gets a lot simpler. You just work out your vectors, you let the math take care of it, and you get a complicated answer. You know, I don't complain when we use symmetry to simplify calculus, which, you know, but I complain when it's the other way around. Where are we going? We're going to do this. We're going to create electric fields using point sources of charge. So if you imagine you have a point source of charge, I have electric field coming off in all directions. And I'm going to construct a Gaussian surface. It's a whole bunch of cards stitched together so it forms this complete surface. I can only draw it, you know, I'm only drawing in 2 dimensions, so it looks like that. And I'm going to ask myself, what's the flux throwing through this surface? And what I'm going to find is that the flux throwing through that surface will be the sum of all these little calculations that I do. And I'm going to get to the stage, it's not on this page, I'm going to get to the stage where the flux will equal the sum of all these little calculations that I do, and that will equal the charge inside divided by a constant. And that's just like phenomenal, because what that means is if I know the charge inside, I can work out an electric field. And so that's what I'm going to use Gauss's law for. I'm going to develop it, but then I'm going to use it to calculate the electric field at a given point in space in ways that I could not use Coulomb's law to do. Coulomb's law is great, but at some point it's too complicated. This kind of takes over. So that's what we're going to go to next time, okay? Let's call it a day. Did I finish on time today? It's right, isn't it? It should be finishing now.
Yeah.
Cool. So we'll call it a day there, and then we'll continue.